Hello everyone. Today I will discuss the basics for completing a linear programming model using the Excel Solver add-in. This video focuses on how to set up and complete an optimal solution for a company with limited resources. For this video, I use the Galaxy Industries example from the textbook Applied Management Science by Lawrence and Pasternak. To begin, there's a specific way you should address all word problems. First, read the entire problem. Too often decision makers read portions of a problem and then jump to solve it without taking all of the information into account. Next, list what you know. These are called the knowns and help you to determine the process or the equation that you need to solve the problem. After you list the knowns, list the unknowns. These are the items you want to solve, for. Many times the unknowns are followed by a question mark. That makes them a bit obvious, but in some cases there may not be a question mark, and it may be information you need to uncover from the data given or your personal experience. Now you've got enough information to determine the equation or the process that you're going to use to solve the problem, and finally, you're going to solve the problem for the unknown variables. For instance, say you need to solve a problem where A plus B equals C. That's a fairly simple equation, but after reading the entire problem, you look for the knowns. Step 2. Say they give you B is equal to 5 and A is equal to 6 in the problem. For step 3, they ask you what is the value of C. You then know to use the equation A plus B equals C. Now once you have what you know, what you need to know, and the equation, the solution is fairly simple. A plus B equals C. B is 5, A is 6, 6 plus 5 equals C, 6 plus 5 equals 11. Now let's apply this method to the linear programming solution to the Galaxy Industries problem. Now first read the entire problem. Galaxy Industries is an emerging toy manufacturing company that produces 2 space-age water guns marketed nationwide, primarily to discount toy stores. Although many parents object to the potentially violent applications of these products, the products have proven very popular and are in such demand Galaxy has not had problems selling all the items it manufactures. Now, 2 models, Space Ray and the Zapper, produced in lots of 1 dozen each and are made exclusively from a special compound plastic. 2 of the limiting resources are the 1,000 pounds of the special plastic compound and the 40 hours of production time that are available each week. Galaxy's marketing department is more concerned with building a strong customer demand base for the fledgling company's products than with meeting high production quotas. 2 of its recommendations, which Galaxy's management have already accepted, are to limit total weekly production to, at most, 700 dozen units, and to prevent weekly production of Space Rays from exceeding that of Zappers by more than 350 dozen. The table shown on the slide summarizes the per dozen resource requirements and profit values. And those profit values are essentially calculated by subtracting production costs from the wholesale selling price. Now you can kind of see how it's easy to be overwhelmed by a word problem. Now using the elephant metaphor, let's begin eating it one bite at a time. After step 1, reading the entire problem, we go to step 2, identifying the knowns. Now, from the first graph, good in here, but not can use for the optimization problem we need to solve. In the second paragraph, we know there are 2 models, the Space Ray and the Zapper. The metric for the lot size is 1 dozen each. Important to the number of toys we can manufacture is the amount of special plastic available and the 40 hours of production time. Now write down the knowns as you find them as you read through the problem the second time. So right now what we've got lot size 1 dozen and 1,000 pounds of special plastic limit with 40 hours of production time each week. Going back to the problem, from the third paragraph, we know a little more about the company, which can help us when we make a recommendation, but it really doesn't affect this problem, other than the decision to limit weekly production to at most 700 dozen units, as another known, and to prevent space ray production from exceeding zapper production by more than 350 dozen. Adding that and the information from the table to our list of knowns, this is what we come up with. And these are the knowns that we're going to use to calculate the answer. Once we have the knowns, we go to step 3, identifying the unknowns. Although that it's not clearly a problem, we can infer the industries wants to maximize profits while meeting manufacturing constraints that they've already approved. So step 4 is to determine the equation or the process that we're going to use. So we obviously need to design a linear programming model to maximize total weekly profit. Step 5, let's solve this problem. This is where many decision makers have problems because they're not proficient in identifying variables and constraints. They deal more in vague, broad brush definitions of critical variables rather than concise, quantifiable, measurable metrics. I strongly recommend you complete each step of the linear programming process, no matter how simple it may seem. Jumping steps can cause you to arrive at the wrong answer. Now, based on the reading of the problem and the knowns we identified, there are 2 critical variables we need to consider: the number of space rays and the number of zappers produced, in lots of a dozen, of course. Since we earn $8 of profit on the space ray and $5 of profit on the zapper, the objective function would be to maximize 8 times x sub 1 plus 5 times x sub 2. It helps to identify the variables in terms of the letter x, so we write this as maximize 8x sub 1 plus 5x sub 2, where the number of dozen units produced is x sub 1 for the space rays and x sub 2 for the number of zappers. Now don't get overwhelmed yet. I know we're throwing x's around, but just look at how this falls into place when we enter the knowns that we wrote into the Excel spreadsheet. So once we've determined what we call the objective function here, which is to maximize the number of space rays and zappers, we move to the constraints to apply the process. And these come from the knowns that we identified a bit earlier. So we look at the limitations of each of the constraints and enter them into the frequency table that we're going to use to solve the problem. Along with the identification of the critical variables, this is another important step that affects the answer that you get. So the mathematical model becomes what we just saw with the profit to maximize 8 times x sub 1, the space rays, plus 5 times x sub 2, the zappers. This is the line we usually place at the top of the table, as profit is normally the overriding function we want to maximize. The second line, ST, means subject to. In this case, the profit is subject to the constraint identified in the problem. The space ray takes 2 pounds per dozen and the zapper 1 pound. Together, the total plastic used cannot exceed 1,000 pounds. We get that straight from the mathematical model of the knowns that we produced. The next constraint, subject to the time, takes 3 minutes, 3x1, to produce a dozen space rays and 4 minutes to produce a dozen zappers. So 3 times the number of space rays, x1, plus 4 times the number of zappers, x sub 2, cannot exceed 2400 minutes. We had 40 hours, 60 minutes per hour, 2400 minutes. So we need to keep all the measurements consistent, so hours have to become minutes. If we talk in production in minutes, we have to talk about the constraint in minutes. This constraint shows the total production must be less than 700 dozen units. Remember that 1 times the dozen zappers plus 1 times the dozen space rays has to be under 700 units for the week. By convention, we do not normally show the number in front of this when it's equal to 1, but I include it because it refers nicely to the table in Excel. This constraint shows a mix that they want to maintain. Notice the sign is negative rather than the addition function from the previous constraints. We'll discuss the technique to enter negative number when we look at the Excel table. The final constraint is more of an IND when choosing items in the solver input data box. You can include this constraint in the problem if you wish, but when you choose the non-negative option in the solver options menu, this is already taken into account. Now you may notice I identify each constraint on the left of this equation. The text shows it in the right. You'll see why we enter the constraints into the Excel spreadsheet. Now let's set up the table in Excel so we can use Solver to find the optimum mix of these toys. If you follow the steps I've shown you, the problem transfers nicely to an Excel spreadsheet. Transferred a copy of the mathematical model so we have it as we enter the constraints. You're going to set up the spreadsheet with a heading at the top cells. In this case, we're going to title the table Galaxy Histories. This is more of a professional formal step. Than a step necessary to the calculation of the answer. It keeps everything straight if you correctly title your cells. The next step is to provide a place for Solver to identify the number of toys to produce. It may seem a bit confusing because we normally put this section at the top of the table, yet we enter it in the second data box in Solver. And I'll highlight this when we complete the entry step. We'll place the cells, the total number for that in row 4. Leave the cells in B4 and C4 empty, as Solver is going to fill them in for us. Next, we need to enter the constraints under which Galaxy must operate. Now these come from that mathematical model that we designed earlier. You place the items in the column associated with the variables we identified, space rays and zappers. Now you remember x1 was the value that we chose for space rays, and x2 was the value we zappers. Now I'm putting them here. You don't put them in your solution. I'm putting them here to help us to identify the columns. Now we're going to add the titles for the 2 cells that we complete that are going to help us to do these calculations. We're going to place titles total and limit in cells D5. Now notice I skipped column E, and that's because we're going to put the relationship of the constraint in this column. So let's start with the profit. Now for the profit, we're going to enter 8 and the 5. We're maxing x1 and x2. Now we're going to enter a sum function into the total cell D6. The reason we do this essentially we want to add the product of the total number of space rays and the total number of zappers times the for each. We're going to use this function for all of the cells in column D, so we need to include the dollar sign before the cells that we don't want to change as we drag the function down. So we're not going to want the number of space rays and zappers to change, so it's $B $4 to $C $4, but then the sum product, where they're going to add them all up, is going to be upon the row that we're in. You'll see what I mean as I complete the table. Now enter the constraints and their limits. Now for the plastic constraint, we've got the constraint was 2x1 plus 1x2. So we enter plastic 2, 1. The sign of the constraint less than or equal to, and the limit, which was 1, comes straight from the model that we did. Next, we enter the time constraint. So for time constraint, at 3x sub 1 is 4x sub 2. Again, it was less than or equal to. So here's a quick trick. If you're going to replicate the information in the cell, grab the lower right-hand corner and drag it down. It gives you the same information in the cell. And then, of course, the limit for time was 2400. 2400 minutes. The next constraint is the number we're going to produce. So for the number, got 1 of the space rays, 1 times the number of space rays, plus 1 times the number of zappers, less than or equal to total constraint of 700 total dozen. The last constraint that we're going to add is the mix, because we had a constraint of the difference between the two totals that we've got produced. And you'll notice the difference, and I'm going to -1 here for zap, has got to be, the difference has got to be less than 350 dozen. The last step is to complete column D by dragging the function from cell D6 down to D10. I grasp or I click on the lower right-hand corner and just drag down. You'll notice that, and it's a good idea always to verify the numbers in the spreadsheet match, but you'll notice that the profit is B4C4 times B6C6. Plastic would be B7C7, time B8C8, number B9 and C9, and the mix B10 to C10. It's a good idea to save your work periodically, as you don't want to have to go through all the processes multiple times in the case of a gremlin attack. Now the values appear correct, so let's go on to the next step. Now assuming you've already activated the solver add-in, and if you haven't, no problem, just see the video about activating it for linear programming before you go any further. Let's open the solver data parameters box. Now since I'm using Excel 2013, the solver add-in is located in the data tab. I open the solver box, and you'll notice that this input box is a bit different than the one in the textbook. But the boxes are essentially the same. We're going to begin by focusing on the box identifying the target cell, or the objective for later versions of Excel. And you're going to ensure that there's blinking inside that cell and that the cell was blank before you start. You notice that I deleted what was in there before so that I've got all blank cells. For the objective, we want to maximize profit. Ensure the cursor is blinking in the objective cell. The data box is blank. And then we're going to choose the cell for total profit. This is what we want to maximize. Cell D6. We're going to make sure that the maximum radio button is on and move to the changing cells box. This is where we enter the cells that affect the total profit, which are the number of each product manufactured. Ensure the cursor is blink box and that the box is empty. And we're going to choose the cells for the total number of toys manufactured, cell B4 and C4. So essentially from that sum product function, we're looking at altering the number of the different toys to give us the best total profit. Now we're going to enter the constraints. I'm going to show you two methods. The first is entering each constraint as a separate entity, and the second is a time-saving method, entering all constraints with the same sign at the same time. You do not need to use the more advanced method until you feel at ease with the process. First, each constraint one at a time. We're going to click on the Add button to the right of the subject of the constraints box. This is applicable to each constraint and the relationship. You need only click a cell and the information transfers into the box. So here, let's start with, we've done profit, so we don't need to do profit again. So for the plastic constraint, we're going to go here and the cell reference is going to be D7, the sum product cell. The sign is less than or equal to, and the constraint for plastic is 1000. You can either click OK and then click Add again from that main box, or just click Add, moves you to the next line. We do this for each constraint. We did plastic, so for time, we click in the total cell, complete the sign, and the constraint is 2400 minutes. For the number, we click in the total number cell, recognize the relationship between that and the constraint, and then click on the total, the limit, which is 700 number. Click up, we got it. We're going to click on the mix, recognize the relationship, and then the constraint is 350. Now we're going to check that all cell identifications are correct, and we're going to verify the options under which we want to calculate the answer. We've got the objective total profit, changing total number of toys, and then each one of the constraints: plastic, time, number, and mix. For these problems, we're assuming a linear model and non-negative values. Choose simplex LP linear problems, and when we choose this option, we can then generate the what-if reports, sensitivity, and answer reports. Now you're ready to calculate the maximize function for the problem. Click on the Solve button, in the lower right-hand corner of the box, and Now, when Solver finds a solution, it tells you so in the Solver results. And if the conditions are not satisfied, the program tells you so, and this report box will be gray. Choose the answer and sensitivity reports and click OK. Show in the cells of your spreadsheet. To maximize profit, $1,360, we need to put 320 dozen space rays and 360 dozen zappers for each week. Notice that each of the or constraints is satisfied. We use less than or equal to 1,000 pounds of the plastic. We use less than or equal to the maximum amount of available. Then to make. The difference between the mix is 40, which is less than the 350. Now the reports show on separate sheets. You can access these reports by tab at the bottom of the worksheet. The answer is used to determine the slack for each constraint and whether or not the constraint is binding to the outcome. The status is binding if there is no slack and not binding if there is slack. The sensitivity tells us what happens if we change the constraints or the objective function. This is a more advanced report best discussed in another forum. Now, the last thing I want to show you is how to enter all the like sign or the same sign constraints at one time. So rather than entering each constraint, we're going to choose the Add button, highlight all the totals with the same sign, and then highlight all of the limits. Once again, we use Solver, and since I've already chosen the objective function, total is not going to change. The variable cells we're changing is the number of space rays and zappers. I'm going to delete the constraints we entered before. Add all of the trace. And you'll notice that now the range of values can equal one individual line for each. Sensitivity reports, same. Now I hope this video makes the linear programming process and understanding word problems a bit easier. Please see the video on linear programming for production scheduling, the video on production optimization, and the video on financial investing. Now, I'd love to hear from you, so please send me the feedback or your request for more videos you'd like to see to my email, theprofessor@professornito.com. And please visit my website for more information and more training opportunities. Have a good day, and as always, happy calculating.